be a good quiz to collect. Well, too late. I've already told you that I'm not going to collect it. So why don't I give you this? We'll give it a try. And remember, one of the reasons why I like to give these is because the test will be similar to this. And apparently the test is April 5th, you said, which is actually a day I'm not going to be here. So I have to decide if I want to do what Dr. Brad is doing. Let me know how things go. And we'll see. Is anyone else in the Dr. Brad class doing this? Ooh, few of you. Very nice. Wow, half of you. Enjoy. Hope it goes well. We should pray for that. But you know what's going on in there here, don't you? So you don't need any prayer. Just keep your brain. Like this. 1, 2, 3. Here's 3 for you. I hope. I don't know if that's 3 or 4 or 2. 1. Oh, here. Maybe you can say one back to me. Excellent. It's so awesome. I hope you can throw these on back here. I think I got them all. Everyone's got one. Good. So give this one a go. I'll put it up on the screen momentarily, and then we'll do it together in about, 10 minutes. I'll give you another 30 seconds. Watch the clock. Try to get those last answers down. Do your best, but we're going to go over this momentarily. All right, your 30 seconds are up. Let's see how we did. Hopefully you're doing this. Might be just stuck on that last one. The last one's easier than it looks. This first one, though, hopefully this isn't too bad. You just changed, I guess we should first check to make sure that this function is a decreasing function. And I suppose I should start at 1 instead of 0. I couldn't tell because when I did the photo of the quiz, it kind of got garbled. So I just went from 0. Same answer you get if you start at 0 as if you start at 1. Well, almost the same. So you change the summation to an integral. That's what the integral test is. And then, of course, because I'm going to do it this way, I have the limit as b approaches infinity of the antiderivative. If you left off the limit as b approaches infinity, I probably wouldn't mark it wrong at this point, because we all know what we're doing, but try to be careful about these things. Anyway, that ends up being infinite, no matter which way you cut it. Even if I had a 1 down here at the bottom, it would still be infinite. And so this thing diverges. That wasn't bad, was it? Let's do the next one. The next one's my favorite function. So let's see, where is it? There it is. So we're doing this integral. So you can always count on this making an appearance somewhere. It just happens so often in calculus 2 because we're dealing with rational functions and series and stuff. Anyway, here it is. Is this thing working? Yes, it is. Sorry, double checking the, so there, that thing is the arctangent. Is this from 1? It is from 1. You get the same answer. Sorry, I don't have my, and this, I mean, this is what the world looks like to me without my glasses on. So, you know, I can sort of see, but not exactly. You can put a 1 down here, you'll get the same, well, almost the same answer. So anyway, I really want to know what the limit as b approaches infinity of arctangent of b is, and that ends up being pi over 2. So whether you have a 0 on the bottom or a 1, you're going to have pi over 2 minus either the arctangent of 0 or the arctangent of 1. Either way, it's a finite number. Since that's finite, and this is a decreasing function, 1 over x squared plus 1 decreases, then this thing converges, and we can be happy about it. This last one, I looked at it, and I thought, wait a minute, am I seeing this wrong? And so I actually had to pull out the piece of paper and find a pair of glasses, and I examined it closely. And indeed, it is exactly the way it is printed here, which means that this thing diverges, guaranteed. You don't have to do the integral test for this, do you? Did anyone look at this and say, why should I bother? I didn't bother. I just wrote diverge. Does anyone know why it diverges without doing the integral test? Some of you do. Yeah, you guys do, Luke?
Not decreasing.
It's not decreasing. And not only is it not decreasing, the limit of the terms is infinite. If you were adding these numbers together, you'd start off with n equals 0, which is 0. Then n equals 1 gives you 4e to the 1/2 power. And then you get 4 times 2e to the second, 4 times 3e to the 9/2. Anyway, those are getting bigger and bigger and bigger. There's no way that that's going to converge. So that definitely diverges. Using the nth term or the test for divergence, I'm going to go over all of these in just a minute, all the tests we've done so far. But anyway, this thing diverges. But I thought, you know what, probably when I was typing this up a year ago or 2 years ago, whenever I typed this up, I probably had intended for this to have a negative there. That's why I had to pull out. Yeah, what do you think, Jackson? Oh, overall question. Yeah, and then we'll, yeah, so let's just finish it. So if this had a negative there, then the story is completely different, isn't it? Because then you would do this, and you would get that, and you would get that. And that one does converge. So, yeah, if this was a negative, then it definitely does converge. Okay, Jackson, what's your overall question about these things?
Can you go over them the line again?
Yes, I can. So with each of these, when you're using if you want to use the integral test, the first thing you want to ask yourself is, does this sequence, is it a decreasing sequence? So decrease, yes. Guess that should be a question mark. So this one does decrease. I mean, if you think about it, 2 over 1 plus 1 is bigger than 2 over 2 plus 1, which is bigger than 2 over 3 plus 1, et cetera, et cetera. So this thing decreases. Then, since it's a decreasing sequence, you're going to do this integral, which I could change to a 1 because I couldn't tell that this was a 1 here. Okay, there. So you do the integral, the limits will be the same as the limits for your summation. And if this integral converges, then your series converges. If the integral diverges, then the series diverges. So all I have to do is I have to do this integral. I need to know what the antiderivative of 2 over x plus 1 is. Well, that's easy. That's just 2 times natural log of x plus 1. So let's change that to a 1 just for fun there. And of course, in my wanting to write this correctly, I'm going to write this with the limit as b approaches infinity. Some of you, I've noticed, you just put the infinity here, and you just think to yourself, I'm going to do a limit as the top goes to infinity. I'll probably overlook that, just to be honest, and I'll just sigh. But I'll write it. I'll just mark it out. But anyway, so this is the correct notation. Anyway, that limit is infinity. And so because this is infinite, it means that the summation will also be infinite, meaning that it diverges. If the summation was finite, it doesn't matter what it is, if it's finite, then the original series will be finite. So they always share the same fate. I don't know if did that answer your question, or do you have something more specific?
More like, how did you know that it's infinity?
I guess because I know that the natural log, so if I was to graph this, the natural log, so basically I'm looking for the limit as b approaches infinity of that natural log. That natural log looks something like this. And so as x goes, or in this case b, but whatever, as x gets bigger and bigger, the function values get bigger and bigger. So that is to infinity. And maybe beyond, but what does that even mean? But yeah, you go off to infinity. So it's just because I know what the natural log function looks like. If this was, let me ask you this though, if this was, instead of natural log, if this was the square root of x, square root of b, you would know that that is infinite, don't you? Maybe because as you put bigger and bigger, that's what this symbolism means. Put a really big number in there. What happens to the square root? Yeah, it gets really big. Yeah, so the bigger the number, you put 1 billion in there and you'll get 1 million or whatever. I don't know what the square root of 1 billion is. It's not 1 million, it's like 10,000. But it still increases. Increases without bound. That's what infinity means. It means increase without bound. And because there's no bound, it means that there's no bound for this, and so this diverges. All right, anything else? Other specifics or generalities? Either way. All right, one of the things we're going to do, probably next week. Next week we'll do this, but you should get it started this week. I will try to get you an actual something. You'll want to have something like this. So what we're going to do, you know what? What have I done here? Is this, this is my series. Just a minute, I need to get a new notepad that's completely fresh. I'm going to rename it. This is, okay. Good. Okay, so you can't see the name of this because it's in that black spot up there. I don't know why it doesn't show up. But I've got this. This is series test list. So eventually I'll try to help you get a sort of a way of organizing this. But to start off, I just wanted to summarize what we've done because we're moving on. And each day we're going to be adding a new test or a new fact. So the number one thing, even though it wasn't the very first thing that you do, or that we learned the test for divergence. So I always put that at the very top because that's so easy to do. With this number 3 here, it's way easier to use test for divergence than to use some other test. And the reason is, all you have to ask yourself is, does the limit go to 0? So let me just jot this down. And you're gonna see this, we're gonna add to this, but you're gonna see this over and over again, this list. So here we go, we have, if the limit as n approaches infinity of the term does not equal 0, then the sum diverges. Diverges. That's what the test for divergence says. It is a test for divergence. It is not a test for convergence. Basically, you're just weeding out all the functions or all the series that definitely don't converge. You know, you don't want to have to deal with them because here's the thing is, at the end of this, let me just go down here. I'll go back up to the top in a minute. At the end, we're going to have something like this. 2 to the n over n factorial. N goes from 0 to infinity. So take a look at that. Does that converge? Does it diverge? Can we use the integral test? I don't know. That's a weird, factorial, that's probably got half of you scared right there. So anyway, at the end, we're going to be using this sort of list of flow chart or so to evaluate series. And you want to get rid of anything that is obviously divergent right off the bat, because who wants to have to think about n factorial if we don't have to? So anyway, that's the first thing we did. Well, it's not really the first thing we did, but it's the first thing that you will do when you look at series. Number 2, the second thing that you're going to do is this a familiar series? What does this mean? Here, I'll do this in 2 parts. We have 2a geometric. If it's a familiar series, then you just have to apply whatever rules you know for the familiar series. 2a geometric, what is a geometric series? It is something like this. The sum of a times r to the n, where n goes from 1 to infinity or 0 to infinity, it doesn't matter. And this will converge. So just remember, the rule is this thing converges when r is between 1 and -1, not including the 1 and the -1. Converge. And when r is greater than or equal to 1, or, whoops, I'll put it back there. When r is less than or equal to -1, sorry, I'm blaming it on the time change right now. I think I can get away with it for a week. I get a week after the time change. I was talking to my wife, I said, Beck, right after COVID, I learned that the first week of school, nothing happens. Like, you remember right after COVID, those semesters, I don't know if you were in high school or whatever, but everyone's just trying to get used to, like, what are we doing? How do we do it? So the first week, nothing happens. I'm going to start adopting that for the week after the time change. Nothing's going to happen the week after the time change. Okay, this diverges. Until Marco Rubio wins. Then, and Marco Rubio for president, I'm telling you, he's the greatest. In terms of the time change, he wants to get rid of it too. I don't know anything about the rest of his politics. He could have one plank in his platform. Okay, geometric. So that's the first of the familiar series. We have another familiar series. Another familiar series, it is the harmonic series. I'm not going to write that down though. Don't write it down. Well, you could. Go ahead if you want to. The harmonic series is another familiar series that diverges. But the reason why I'm not going to write it down is because it is one of a family that we're going to be learning about today. And so I'm going to leave that blank for now. But the harmonic series is going to go right here. And that's what we're doing today. So next, number 3. We're almost done, and then we can start the PowerPoint. well, we're almost not gonna, this is gonna have like 8 lines to it, is the integral test. Okay, the integral test is this. If a sub n is decreasing, then, and a sub n is equal to some function, then this integral and this summation share the same fate. And by sharing the same fate, I mean that if one of those converges, the other one will converge, and vice versa. So this is what we did for homework for today. Hey, so far so good. And actually today we're going to do another aspect of the integral test, but we're only going to add one thing to my little chart here. So the chart is only going to get one thing bigger, and that is I'm going to fill in 2b. That's all. There's going to be an additional thing that we're going to be doing for Monday on the homework, but there's not a lot that we're doing today. So, but each day you should expect another something to be added to this list until we get done. Maybe the next exam is when we'll stop adding to this list. You'll be so thankful. But anyway, let's switch to the PowerPoint. Do I have it here? I do. There it is. Okay. So first things first, let me find it. I'm out of order here. Is it here? Estimating the sum. I don't care about that. Where is it? Oh, here it is. Yeah, okay. Well, I guess I have the rule there. Don't even write that down. There's too many words. This came from a textbook that I used to teach out of. But this is the integral test. So the integral test says this. So basically, if this converges, then this converges. If this diverges, then this diverges. It's the same as saying that they share the same fate. Of course, we have to make sure that we have a positive decreasing function from the get-go. So here's the cool thing about the integral test is the integral test allows us to very quickly and easily evaluate a particular class of functions, a class of series. So I'm going to just switch back here to this for a moment. And in fact, I'm going to keep that as clean as possible. So I'm going to switch back to this. Okay, so here are some series that you will notice are very similar to one another. Here's another one. N equals 1 to infinity of 1 over the square root of n. Give me a sec here. I'll write down a couple more. N equals 1 to infinity of, I'll put a 3 up there just to make it more fun. N squared. Okay, almost done. This n goes from 1 to infinity of maybe a 7, why not? Over n to the 5th, but this is going to be the 7th root of n to the 5th. How about that? Now I hope you can kind of see what is the relationship between all of these. These all have the same sort of basic form. You all have a constant over n to some power. So each one of these has a constant over n to some power. And so because of this, we call these P series. I know, why can't we call them power series? Well, there's another thing in math that's a power series, and so we can't call these power series. These are called P series. Give me a sec here. I'm going to put them here, and I'll go back to the PowerPoint momentarily. These are called P series. And here's the general form of a P series. So there it is. It's just something over into a power. The P represents the power. Oh, I should do one more. Just a minute. I just realized this will be fun. Let's do this one. Just to add to the list, add to the intrigue. How about this? N goes from 1 to infinity of 3 times the cube root of n. That's a good one. That's also a P series. You might say, well, how is that a P series? Well, let me show you why these other ones are p-series, and then we'll get back to the PowerPoint. So over here, this one is a p-series because you have n to the first power, and so p equals 1. I don't know why I just changed over to my crayon, but that's what we're doing now, apparently. Okay, so your job is to tell me what the value of p is for each one of these. What about this one? I'll do the second one for you. See how kind I am? This is 3 over n squared. Oh, p is equal to 2. How about that? That was easy. You get to do the hard ones. What about this one? Let's see, I'll pull out the volunteer list here. I know you're all excited. Just a sec. Here we go. Where is the volunteer? Oh, there you are. So many happy faces on here. Jackson. Jackson, do you know what p is for this 1 over square root of n? So if you wanted to write square root of n as a power, what's the power you would use?
1.
Perfect, that's the p. This is equal to 1 over n to the 1/2. And so the p here is 1/2. Notice that the p is not negative 1/2. It's tempting to say that the power there is negative 1/2, but the problem is that the way that we write p series is like this, where it's something over n to a power. So the power is the power that's in the denominator. Like there the power is 2, here the power is 1. Hey, there the power is 1/2. Perfect. All right, what about this one? What is the power? Ooh, that's a weird one. I'll bet you know, though. Give you a sec to think about it. Adric, what do you think of the power for this one?
5 over 7.
It is. Very good. P is 5 over 7 because this is just n to the 5/7. I know, it's so hard. We have to deal with this algebra and these powers, and I mean, basically, you're going back to algebra 2 here, I feel. But anyway, yeah, the power there is 5/7. Very good. So, what does this do for us? Well, back here, what we can do is we can take that p series, and let's do this once and for all with the integral test. Here's what I mean. Take this p series and do the integral test with it, which means that we're going to compare this with this. Okay, this is going to be, oh, here. I'll do one more thing to make it easy for you, because I do have compassion. How about this? Does that make it a little easier? I know it's hard with the letter. The p there, if it was just the number 2, you'd have no trouble with it. But given a p, that's hard. So I'll write it like that. I think you can handle it now. Madison, do you know the antiderivative of x to the negative p? So it's just a power. What do you do when you have like if it was x squared? Like, here, let me go here. We'll give Madison this one. So what would be the integral of x to the 5th? X to the 6 over 6. Where'd the 6 come from? Add 1. Add 1 to the power, right? That's what the rule is for doing integrals of basic polynomials or powers of x. And this is just a power of x here. Cooper, do you know what the antiderivative of x to the negative p is?
X to the negative p plus 1 over negative p plus 1.
Very good. So, sorry it keeps bouncing around, but this is going to be x to the negative p plus 1. So just like down here, Madison did 5 plus 1 and got 6. This is whatever negative p is, plus 1, and then divide by negative p plus 1. And this is going to be evaluated from 1 to infinity. So the problem child here is the infinity, isn't it? The 1, we still don't know what p is. You might be worried about, well, what if p is 1? Well, if p is 1, then we would have to do the natural log, because you'd have 1 over x. So let's just assume P is not 1. But let me go ahead and plug these in, and I know that this is going to be a little bit, I don't know, this is not quite proper, but I'm going to do it anyway. Negative P plus 1. Oh, 1 to any power is just 1, isn't it? So let's see, what can I do to make that go away? Hold on a minute. I feel bad about that infinity over there. You know what? I can't do it. Sorry, I tried, but I can't. Limit as b approaches infinity of this. Okay, so here's the thing. We're dealing with this limit as b approaches infinity of that limit. So the question is, and I know this is hard because we're thinking generally, we don't have a specific number for p. What I want to know is what values of p, for what values of p will this thing converge, and for what values of p will this diverge? Let me just give you an example so you know what I'm looking for. If I used p equals negative 1, then what I'd have here is I would have basically infinity to the negative 1, or the negative 1 plus 1, which is infinity squared. Darn it. Infinity squared. So I just don't like writing infinity to a power. But anyway, if this p was negative 1, then you'd have infinity squared, which is infinite, diverges. If, on the other hand, I had p equals, say, 5, then you have infinity to the negative 5 plus 1, which is infinity to the negative 4. That's 1 over infinity, which is 0. So you're good. So does anyone see where the dividing line is between convergence and divergence? So that's all. Once we get that, then you can forget about all this. Oh, you got it, Caden? If it's negative, you're going to diverge, and if it's positive, it'll converge most of the time when it's positive. I believe you with the negative. So if you put a negative number in here for p, then you'll have infinity to a positive number, which is big. What if you put 1/2 in there for p? What happens there? If p is 1/2, then what you have is you have infinity to the negative 1/2 plus 1, which is the square root of infinity, which is still infinity. So positive 1/2, you're going to diverge. There is a dividing line, and the dividing line happens to be at 1. If your p is bigger than 1, you're going to converge. If p is less than or equal to 1, you diverge. Anyway, here's the rule right there, and I'm going to copy this over to my thing here. Just a minute. I know this is annoying. I'm just going to switch back to my series list. And I'm putting this under 2b. Number 2b, this is going to be one of these series that we're going to say this is familiar because after today it will be. These are p series. And so you have something like this. N equals 1 to infinity of a over n to the p. And this is going to be, if p is greater than 1, this will converge. If p is less than or equal to 1, it's going to diverge. So p series is going to be a familiar series after today, hopefully. All right, let's look at some examples of p series. We can flash back to this if need be. But on the next slide, here's 3 p series. And I want to know which of these converge, which of them diverge. Maybe they all converge, maybe they all diverge. So to do this, I'm going to be asking you 2 questions. Number 1 is the most important one. What is p for each one of these? What is the value of p? What is p? What is p? So start with that, and then once we've nailed that down, we can ask whether they converge or diverge. All right, Rachel J., what's the first one? What's the value of p?
3.
It is 3. Look at that. It's a 3. All right, so Sawyer, you knew that that was a 3, didn't you? Excellent. Does that converge or diverge? Gotta check the list. Here, you want me to put it up here? I can go back one. It does converge because p is greater than 1. See how simple that is? All you have to do is identify the p. Once you know what p is, then 3 is greater than 1, which means this converges. That's all you got to do with the p series. Just say, what is the value of p, and then does it converge or diverge? All right, let's do the next one. Luke, what is the value of p for this second one? All right, I will give you the fraction, but I won't take the 1 or the 3. Yeah, no, I gave you the hard one. Yeah, this one's hard, isn't it? Because you have to think in terms of exponents and radicals and what do they do. Here, if I had rewritten this like this, it is 3/2, by the way. If I had written it like this, 1 over into the 3/2, that's too easy, isn't it? But it's the same thing. You have to remember that a radical is just a fractional exponent. So this radical is x to the 1/2. This radical here is x to the 1/5 because it's the 5th root. So when we get down there, just be aware you're going to be doing a 5th root. But anyway, p is 3/2. So we're onward to Matthew. You knew that it was 3/2, didn't you? Excellent. Does this thing converge or diverge? It does, because 3/2 is bigger than 1. That's all you have to do is compare this with 1. So this thing converges. Converge. Yay. Okay, last one. We need a P for that one. Who are we up to? Ethan. Ethan, do you think you can tell me the P for that one?
Is it 3/5?
It is. So that one's extra confusing because I've got that radical encompassing the entire fraction. I'll write it a better way in just a minute, but yeah, you're right, it is 3/5. Let me rewrite this just slightly so that you can see. This is the sum of 1 over the 5th root of n cubed. So there's another way of writing it, because when you have a 5th, wow, this green is so bad, I'm sorry, I'll change colors in just a minute. Anyway, the 5th root of 1 is 1, the 5th root of n cubed is the 5th root of n cubed, and certainly you can write that as n to the 3/5. The radical is the fractional part, the denominator. Anyway, there it is. So we're almost done. Logan, does this converge or diverge? So remember, you're just going to compare the p with 1. Is that bigger or less than 1? Okay, so does that converge or diverge? Let's go back one slide. It's in that blue box up there. It diverges when p is less than or equal to 1, and so this is less than or equal to 1, so this diverges. Isn't that easy? It's so awesome. Okay, so that gives us our p series. Now there's one additional thing that we're doing today, though. So I promised you that we're going to go back and look at the integral test again. And that additional thing is to ask the question of how close we can get to the actual sum based on adding up a certain number of terms of a series. So you can never add up every term of a series. Well, there are techniques that we're going to use, but you have to stop somewhere if you're doing it on your calculator, because you can't sit there all day punching into your calculator and hoping to get the right answer. So what you're going to do is, instead, we're going to approximate the sum using a partial sum. So we're going to add up, and then we're going to stop at a particular point, and then using the integral test, we can actually tell how close we are to the truth. So think of this infinite sum as being the truth, and then if we stop somewhere, we're going to do an approximation. How close are we going to be to that truth? So, yeah, there's so many words here. The remainder is what we're interested in. I just care about this, so I'll just put that there. That the remainder is the stuff that we're not adding up. So if we were to add up all the numbers up to a sub n, then the remainder is the other stuff, the stuff that we did not add up. And it turns out, using the integral test, using a sort of similar idea to the integral test, that if your function is decreasing, then this remainder, so this only works when your function is decreasing, for the right direction for you, then the stuff that you aren't adding up is going to be less than or equal to the integral. You can kind of see the picture here. So here's sort of, let me write this up here. We have, oh, I said that I was going to change colors. I will right now. That we have the partial sum, a1 plus a2 plus a bunch of dots plus an. And then you have the truth, I'll just write it like that, is the partial sum plus the remainder. So the truth is the whole series, the entire thing. So this remainder, if the function is a function that decreases, is always going to be less than or equal to the integral of the stuff that we didn't add up. So let me just show you how this works in an actual example. Let's suppose you want to approximate the sum of this series by using the first 10 terms. So that means I'm going to add up on my calculator 1 over 1 plus 1 over 8 plus 1 over 27 plus 1 over 64. You get the picture. In fact, I've got it written here, right here, there. So 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, etc. So I just want to know the first 10 terms. Don't worry, I'm not going to make you punch this into your calculator. I just want to show you how this works. So when you punch those in, you actually get this number approximately, because even that is an approximation, 1.197. So how close is that to the actual value of the sum as n goes from 1 to infinity? If we were to add up all of them, how close are we? Well, this function, it's a p-series, so we know that it decreases. 1 over n cubed is a decreasing function. So I can use the integral test to approximate how far, how much I'm missing. So let me go ahead and do that. What I'll do is I'll call this the remainder. R10 is going to be less than or equal to the integral of the stuff that I'm ignoring. So I go up to 10 with my adding, and so everything beyond 10, so from 10 to infinity, that's the stuff that I'm ignoring. And so the remainder, or the error, if you will, is just the rest of the integral. This is an easy integral. Whoops, I should change that to x. 1 over x cubed. Let's go ahead and compute this. This isn't bad. Let me find my pick me. Pick me. You all want to be picked. But in particular, Drew is dying to tell me what the antiderivative of 1 over x cubed is, don't you? Woohoo! Very nice. Go ahead. Oh, that's so beautiful. He did it all in his head. Yeah, I thought I might have to help him. Maybe you need some help. This is just x to the negative 3. So very nice work. So you add 1 to negative 3 and you get negative 2 for your power. And then, of course, divide by the power. And he even simplified it. Nice work. And this is going to be from 10 to infinity. I'm just going to rewrite that one more time to make it look a little bit more obvious, hopefully, as to what's happening. Going from 10 to infinity. Now here again, I'm waving my hand a bit. I should be doing a limit as b approaches infinity of this. But I think we all know what's going to happen, that if you do the limit as x or b approaches infinity of this thing, you get 0, because you have 1 over basically infinity. So the upper limit of this thing will be 0. The lower limit will be negative 1 over 200, which is 1 over 200, which I've run out of room. It's 0.005. I'll put it over here. I'll put it in a different color. That'll make me feel better. 0.005. That's how big my error is if I just add up the first 10 terms. It's as bad as it gets. So it's going to be better than, I mean, that's a pretty, so I'm within 5/1000ths. So the very worst is this could be 1.19, 2.5, well, no, it's not gonna be less than this, it'll be bigger because I'm leaving off a bunch of positive numbers. So the very biggest it could be is 1.2025. Yeah, because that would be that much more. All right, that's not bad. There is one last glitch that I need to tell you about. So if you're looking for the remainder, you just change it to an integral for the stuff that you're ignoring. But this is the last little glitch, and that is, suppose you're not satisfied with being within 0.005. Let's say you want to be even closer to the truth. Well, let's ask this question: how much further would I have to go to make sure that I am within 0.0005? Notice I've got an extra zero there. Well, in this case, all I have to do is I have to think in terms of this remainder being less than or equal to the integral. And so this is the important, well, and this, of course, is the function that we were working with, but you'd put whatever function you're working with here. So I want to make sure this remainder is smaller than or equal to this. And if you do that integral, in fact, that's too much has been done. Like you might not, you have no idea where some of you know where the 1/2n squared came from, but I'm going to cross it out just so that you don't think that it came out of magic. It is not magic. It is this: 1/2x squared evaluated from n to infinity. So where did the 1/2x squared come from? It came from Drew. Remember, Drew told me this just a minute ago. Okay, getting back to this. Now I can just plug in my limits. We already know that when you do the limit as x approaches infinity of this, you get 0. And so this is going to be 0 minus -1/2n squared. And that equals 1/2n squared. Because the two negatives make a positive. Now I want that to be equal to this. So let's do a little bit of algebra. It's not bad. 2n squared should equal 0.0005. So you know the drill here. You're going to multiply both sides by 2n squared. And then divide both sides by 0.001. And you get 1,000 is equal to n squared. And so n is the square root of 1,000. The square root of 1,000 is like 31.8 or something like that. But we don't want to add up a fractional number of these terms. So instead of going to the term 31.8, we can't, in fact, there is no 31.8 term. These are integers. We're going to add up the first 32. So I'll use n equals 32, and then I'll be able to be within 0.0005 of the truth. So anyway, that's it. You have a few homeworks. Remember the P series, that's the important thing, and then this remainder business. We can always pick up the pieces on Monday. Do your best. We'll see you on Monday.